entire year that you're going to learn in geometry. Well, technically 2020, right? But this is the last section that we're going to learn. This is the last of the new material, and we're going to do 6.7. So it's actually a really easy section. So let's go ahead and get started, okay? So here we go. All right, so what I want to talk to you about in 6.7 is called perform similarity transformations. So it sounds very, you know, I don't know, very fancy, but it's not very fancy. So I want to think about something like, let's say, whoa, I can draw a star. Let's say I draw a star. Okay. Oh, thanks, technology. And I take that star. Really wants me to make a little star, people. All right, I take that star and I take it to the copy machine and I make it bigger. Okay, if anybody's played with a copy machine before, this is kind of fun, right? I make a bigger star, and then it really wants me to make this tiny star, people. So I guess we're going tiny star too. I don't even know if you can tell that's a star, but hey, that's a star right there. So what we're talking about in 6.7, it's called, again, perform similarity transformations, but it's really about this. So we have some original image. We have an original image, right? And we can do things to that shape that make it similar but bigger or smaller. So we've been talking about similarity this entire chapter, right? Similar figures have the same shape, but they're different sizes. They're two triangles and the original triangle is smaller or the original triangle is bigger. But what's true is that the sides are proportional and the angles are equal to each other, right? So when we talk about that in kind of a general sense, when we're talking about similarity transformations, we have our original. And when we go from our original to something that's larger, we call that an enlargement. I'm sure you've heard that word before. It's probably on a copy machine or Photoshop or something you've used it for. So you take an original and you make it bigger, and it's an enlargement. We don't change the shape of the star when we enlarge it, right? We just change the proportions of the star. All the proportions are bigger, right? So we call that an enlargement. And then sometimes we take something and then we make it much smaller. Yes, this is a tiny little star over here. And when we take something, we make it much smaller, we call this a reduction. This is a big time reduction, but my computer really wanted me to make a tiny little star like that. So that's where we're at. So we have something called the original, enlargement, and reduction. I think those all kind of make sense. And in geometric terms, what we call those dilations. So a dilation is a transformation that stretches or shrinks a figure to create a similar figure. So again, we're not like warping it in any way. We're keeping the same proportions. We're just stretching it or shrinking it. Stretching, we're enlarging. Shrinking, we're reducing it, right? Okay, so that's what we're talking about. We're talking about dilations. And then when we kind of talk about this in a general sense, we talk about something called a scale factor. Now, you'll recall on your quiz, you had questions about scale factor. It's kind of the same and a little bit different. So we call the dilation that we're going to do the scale factor, and we indicate that by the letter K. K is the ratio of the side length of the image to the corresponding side length of the original figure. Okay, so that's how we define the scale figure. Or the scale factor is the ratio of the side length of the image to the corresponding side length of the original figure. So what I mean by that is, so let's say in my original star, this side length is 1. That's supposed to be a fancy 1. Okay, and my new side length is 2. All right, so if I compare my scale factor K is the ratio of the side length of the image to the original figure. So it's 2 to 1 or 2. Okay, so this would have a scale factor of 2. All right, so it's kind of a little bit weird. We use scale factor in one way with a ratio. Its scale factor is still a ratio, but we tend to make that ratio out of 1 when we're talking about the letter K. So for this enlargement, it has a scale factor of 2. So we say K equals 2, and it's an enlargement. If I'm comparing over here to my tiny little star, right? I have no idea. If my original was 1, my new one here is like, I don't know, 1/10 or something like that, right? That's my new side length. So my K, my scale factor, would be the image, the new side, to the original, right? My original was 1, my new is 1/10, so my scale factor would be 1/10. So this little baby star is 1/10 of my original. The enlargement is 2 times my original. So kind of a way that we use scale factor. It's a little bit of a tweak on that, but that's the idea of what a scale factor is. So the deal with scale factor is that we define a reduction. I wanted to switch to red. A reduction, remember we're going to the smaller star here. A reduction is when your dilation, a dilation where K is less than 1 and greater than 0. So you can see here, we reduced our original by 1/10. So we call that a reduction. The dilation is less than 1, right? An enlargement is any time where your K is greater than 1. So that makes sense. Anytime that you have a K value of greater than 1, you're making it bigger. So we doubled the size of the star. If we'd had a K factor of 10, a scale factor of 10, that would be 10 times as big. Okay, so it's pretty easy peasy stuff. I feel like it's intuitive, like it makes more sense as a scale factor when we talk about it in this way. All right, so then, but wait, there's more, right? All right, so you'll recall at the end of the last chapter, we talked about transformations when we were shifting an image on the graph. We weren't changing the size of the original figure, right? But we shifted it around. So last chapter, if you recall, we had something like X, you have an original XY, and say you move your figure 2 spots to the right on your graph, you would do X plus 2, and 3 spots up. The transformation would be your original XY goes 2 to the right and 3 up. Right, so we call that, that's just a translation where we're moving it on the graph. So similar to that, we're going to talk about how do we indicate a dilation. So dilations are actually really easy. So it says you can describe a dilation with respect to the origin with the notation xy equals k times x, k times y, where k is the scale factor. So it says if, so k is the scale factor. So in this notation here, let's say this coordinate right here, that coordinate right there was 2, 3 on my coordinate plane. We weren't on a coordinate plane, but now we are. So originally we were at 2, 3, okay? If I was using coordinate notation for a dilation, my original spot is at 2, 3, and I want to do an enlargement of 2, right? So k equals 2. That means that my new spot of my dilation would be 2 times 2, that's a multiply, 2 times 2, and 3 times 2. Or 4, 6. So my new coordinate on my enlargement would actually, for that point, would be at 4, 6. So you literally take the scale factor k and you multiply it by the coordinate to find out where the new spot is. Okay. Similarly, if I could find this tiny little point on here, I know, I would multiply everything by 1/10, right? So my new coordinate would be 2/10, 3/10. So I took 2, 3 and multiplied each one by 1/10, and my new spot right there would be 2/10 and 3/10 if I was doing a reduction. Okay. And then if you want to fill in the blanks here, we kind of already talked about this, but it says if k is less than 1 but greater than 0, the dilation is a reduction. If k is greater than 1, the dilation is an enlargement. All right, so there we go. It's a pretty easy section. Like I said, you're going to kind of play with dilating things. So now we know that a dilation keeps the same shape. It just stretches or shrinks it. It keeps it in the same proportion. It's a similar figure, right? And then the scale factor is k, and that describes the ratio of the side length of the image to the original figure. So I have over here a little coordinate plane, and I just wanted to do one problem with you just to make sure that you would understand what we're doing. It's actually the first problem in your homework for 6.7. Number 3, and it says that draw the dilation of a polygon with the given vertices using the given scale factor. So Number 3 has coordinates at a equals -2, 1, b equals -4, 1, sorry, and c equals -2, 4, and we have a scale factor of 2. So knowing that we have a scale factor of 2, I know that's going to be an enlargement because I'm doubling all the sides, right? All right, so first thing you want to do is plot your original spot or original figure. So A is at -2, 1. That's A right there. B is at -4, 1. And C is at -2, 4. 2, 3, 4. There we go. There we go. So that's my original figure. I would put my A, B, and C on there, but it's going to be really small, hard to see. So if I want to find the new coordinates, my A prime, my new coordinate is going to be 2 times each of these, kind of like the distributed property, right? So 2 times -2 is -4, and 2 times 1 is 2. B is 2 times -4, which is -8, and 2 times 1, which is 2. And my new C prime is going to be 2 times -2, which is -4, and 2 times 4, which is 8. So if I go ahead and plot those, my new A is going to be at -4, 2, right here. My new B is going to be at -8, 2. And my new C is going to be at -4, 8. 2, 2, I think I did that right. Okay, there we go. So here is my enlargement. The black is my original triangle and the green is my enlargement, right? It looks like the triangle has doubled in size, and that's good because my scale factor is 2. So every side should be twice as long, right? So that works out, I think, if I counted my numbers right. You have to double check my numbers, but you get the idea, right? I've enlarged it. I think the interesting thing is, and I wanted to point this out, I pointed this out in class too. The interesting thing is that when you're performing a dilation, so either a reduction or an enlargement, it's from the origin. So I don't know if you notice that over here in this little thing, it says is with respect to the origin. So basically, you're enlarging this from the center. So what feels like my gut feeling is that this green triangle should just like, you should take the black triangle and it should like zoom out, and the green triangle should be like equal distance away from everything. But because we're enlarging or reducing from the origin, it's always going to be with respect to the origin, how it's at. So if I had, for example, in this problem, had a scale factor of 10, right? I'm going to get a 10 times bigger triangle, but it's not even going to start, my corner isn't even going to start to like way out here on the coordinate plane, right? Because of how you're working against the origin, like that's your center point, that's going to affect where it ends up. So pretty easy other than that. Again, scale factor and kind of relating that back, again, your scale factor is always going to be the image compared to the original. All right, so just to kind of double check that for you, the image, the new image here is the green triangle, right? And that has a side length of 4 down here. My original has a side length of 2. So my scale factor is the ratio of the image to the original, which is 2. So kind of a little bit different with scale factors, but kind of the same idea. So that is the last section. You have officially learned everything that you're going to learn in 2020 for geometry, except for when you do your homework and your test. But if you, again, had any questions, send me an email and I'm happy to help. Take care, guys. Bye.